research and publish that information, but I would dare say that most of the tens of thousands of soil samples that come from on farms, Alan has taken himself. So Alan, really pleased to have you talking to us about soil health, separating fact from fiction.
Thank you, Dr. Smith. Well, welcome. Good morning, everyone. Thank you for having me here. It's a humbling experience for me. I'm honored to be here. I'm, of course, disappointed to have to follow Ray Archuleta because he's already set you up, and how could you follow him? I do believe that it's important for us to change the way we think also. Groupthink is a real issue, and it is something that we deal with in the sciences too. It's as Dr. Pasture, Dr. Louis Pasture, had a difficult time in his career. I think all of those that try a different path are also challenged by the difficulties that we face. So I was given the title of separating fact from fiction. I don't know that I can convince you on one way or the other, but fiction is something that we build in our own minds. I believe that observations are what create facts. Facts are what we observe all the time, and if we can get them to have the same pattern, as Ray has mentioned, patterns are important, then I think we're actually getting to the facts. And sometimes the facts are that we're traveling a path that we might not want to travel. And so that means that you have evidence that you could travel a different path. All right, well, I don't know where exactly to begin, but I'm just a poor kid that grew up on a small farm in Nebraska. My path was that I met a beautiful woman, and she was a scientist also. And she actually encouraged me to be in science. And when I just like to say that when I first started my educational career, I was scared to write a paper because I knew I couldn't. And it challenged me to be able to do that over time. And so I had a year of experience in Canada. I was in Georgia for 15 years. I have a home in Georgia, but I had to move to Raleigh, North Carolina. And I say this because the first half of my career was that I was on a research experiment station, much like you have in Kentucky and all over the country that we have research experiment stations. But in the second half, when I was told I had to move to Raleigh, North Carolina, I decided I'm going to take the challenge. I'm going to explore the state of North Carolina. I've been to, I don't know that I can say officially that I've been to all 100 counties, but I've been to more than 90 of the counties. And I've taken soil samples from all of those counties. And I've tried to learn a little bit and also to share and to learn from farmers that I go to their farm, because that's what's really valuable to me, to get that experience. And I want to then bring that information back to you. So part of the reason that I really wanted to be on the program this day was because I went to some farms here in Kentucky and actually took some samples, and I wanted to share some results. I would have liked to have given you a paper report, but time has gone by, and I just couldn't quite get that finished. I hope to do that later this year. All right, I'm going to just give you a little bit of background first about the foundation of soil health. Soil is really important to our planet, as Ray has already mentioned. So these are some listings here. We don't necessarily have to go into detail of it because Ray has already given you that information. Soil is why we are here. We cannot be here without soil. We cannot be here without the sun. It really starts with the sun. The sun is the most important part there. All right, so carbon in the soil. The carbon in the soil is really the driver of all these processes that we're really functioning about. Plants really can't grow well without enough carbon because they have to access nutrients. And if we apply them like we do, chemically, then we can bypass that. But then we have implications from that. But that carbon is actually doing so much more than just supplying nutrients for the plants as well. And conservation approach, I believe, should be our mantra. In America, we came and dominated the landscape. And unfortunately, we did it with reckless abandonment. And we need to realize that we have to observe our environment. Wouldn't you want to treat your environment well? Yes, I think that's the goal. Like, we want to have a farm that's better for our children than what we received. I think that's all of our goals now. If we have degraded land, our goal should be actually to improve it. That's what we should do. And if we have an improved farm, let's keep it that way and just make it functioning. Because in the end, we all live and we die. We all go back to the soil. We are part of the cycle of nature. And this is, we have to live in accordance with that. And so, make your life good. Soil quality and soil health has a lot of things that we can measure. This is a long list. I don't expect you to read all of the names there, but all of these things can be measured. And that could be important in certain cases. And if it's something that you're really interested in, you can find somebody to actually measure these things. And that's all good. But we separate them into chemical, physical, and biological traits. And they can be all good. In general, the chemical part, where almost all land-grant universities had a state soil testing lab at some time in their lifespan, we focused on the chemistry. Although the physical we can see, like the texture and the aggregates and the bulk density, all of those things aren't really measured in a testing lab, though. We only focus on the chemistry. Now, fortunately, we have more labs that are looking at the biology because we realize that the biology was a forgotten attribute and that we need to look at that a little bit more. I think the NRCS actually made a great leap. They went ahead with kind of calling this soil health because they realized that the biology was missing. And so biology is an important aspect. And so you can really only have health on something that's living. So the living, just like we have human health and we want to have good health, the soil should have good health as well. And so the focus on soil health is relevant, but I think it was a very big leap for NRCS to do that. And so the 4 cell health principles are really valid. You want to disturb the soil as little as possible. Now, in a managed pasture situation, disturbance means that animals are actually our disturbance. Their hoof action can create some disturbance. And some optimization of that disturbance might be the better term here. In cropping systems, because it came from cropping systems, we did disturb a lot as the natural kind of thing. So that's why they want to minimize, that's the term. But we want to have diversity in the system. We want to have the soil covered. In managed grazing, we also have the soil covered as much as possible. And that's a really good thing. And that's why I think that managed grazing systems are going to be important. Now, our moderator isn't here, but I'm going to have to really move on because I have a few slides. And I just want to make sure that I get to the important parts. All right. So I'm going to, when I showed you the long list, the long list can be done, and many people have tried this in various labs, but I think these 4 parts are really important. We need to have the routine soil chemical testing. We should not throw that out. We need to know how much phosphorus we have in the soil, because there are some soils that are just really limited in phosphorus, and if you know that, you need to apply phosphorus. Or find a way of applying it. Like I said in the field yesterday, that there are sources of phosphorus we don't typically think about. We have the physical part, and we can measure the infiltration and aggregation. And I think that would be, the aggregation is something that you can send in a sample, and we can do that. The organic matter is the overriding attribute that I think we need to measure. It's not the only thing that we should measure, but it's an overriding one. And then the biological part, the soil test biological activity. It's something that we can do on a relative good basis. All right, these functions are important. All of these things that the soil does for us, we need to recognize that the soil does do these things for us. We take it for granted, and we expect that, well, it's just dirt, like it can do anything we want. If we treat it like dirt, then it's going to treat us back what we do to it. So all of these things are important, and we need, as scientists, we need to characterize these attributes so that on your farm you can actually have good functioning soil. It's the function of soil that's really important. We want soil to do things for us. Of course, it's a little bit human-centric, but we are society, and we need to gain from. Because we can contribute back to the functioning of the soil. Our management can do that. All right. Now, I believe that challenging the human conditioning is important as well. And Ray, thank you for all of those ideas. And for those of us that are educated in the university setting, we also should be always questioning our teachers and the paradigm. That doesn't mean that we should create a ruckus, though. I'm just saying that we should do it respectfully, and hopefully we'll come to some common ground. Now, there's a perception that tall, deep-rooted grasses will promote deep accumulation of soil organic carbon. Let me just show of hands, how many people would believe that? It's okay. You should believe that. Because tall, native warm season grasses do tend to grow deep. We've seen the image that Ray showed. Dr. Weaver in the Sandhills of Nebraska oftentimes used these images, and we borrow them now from his literature. And they do grow deep, and deep roots are important. They extract water. They're very important. But to associate this is perhaps more of the talk of the fiction versus the facts. The facts are that those roots, though they go deep, they're contributing very little to the actual organic matter in soil. Now, granted, there are acids, and everything happens in its own time and in its own space. But the majority of the effect is going to occur near the surface. Now, this is an image from Dr. Weaver's work where he showed that the roots are very deep in the soil profile, but what you can really see is that the mass, the concentrated roots, are really in the top foot. And he actually made measurements from many profiles, and this is a depiction of those data there, where he actually made the measurements. These are just data taken from his publications, where more than 90% of the roots are in the top foot. Okay, so there's this concept that I want to build on, and I guess this is hopefully my second half contribution to my career and to the science, is that concentration of soil organic carbon below 12 inches is affected primarily by pedogenesis and not by contemporary management. This is the soil forming factors, the things that happen over thousands, millions, and billions of years. The soil has attributes that you have nothing to do with. You were given them, and that's nature. The top 12 inches of soil, though, as a concept, it might be 13 inches, it might be 10 inches. Don't hold me to the exact number, but the top foot of soil, you have some control over. What you do to the land, you're going to be able to change the attributes in that top 12 inches. But below 12 inches, you're going to have very little influence. Now, you can change things because nutrients can leach, and your management can have an impact on the groundwater and all those things. Yes, that's possible, but not on necessarily the carbon or the organic matter. So historical degradative management would have led to low surface soil organic carbon. We see this when we have degraded soils. We have low organic matter. When we talk about less than 1% soils in the southeastern U.S. region, it's commonplace. We see this on tilled land. This is occurring. Okay, bulk density is inversely proportional to soil organic carbon. This is just kind of a scientific assumption that I have to make, is that when we have organic carbon, we actually lower the bulk density. And so we need to multiply those things to get a carbon stock. And this is just an important part. And there's a strong negative association. If you have compaction, you're likely to have low organic carbon as well, because you're just not able to store that carbon and getting it in the soil. And then there's a mathematical fit of soil organic carbon depth distribution that it's relatively accurate. And this is my attempt to associate with my creator, in that God, I believe, it was a mathematician. Many people for thousands of years, they believed in mathematics, and that mathematics does fit nature many times. We have many examples. And in this case, soil organic matter depth distribution fits a natural logarithmic function. Okay, where are the biological resources? So this is a profile. This happens to be in Brazil, but you see the roots there that are penetrating this soil. But in across Georgia, there was a study that was kind of an NRCS-funded project, and they looked at the actual organic carbon under different management systems. And you see here that the cropland, grassland, and forest land were the types of management. But what you see is that the organic matter in this case, was concentrated near the surface, and it declined with depth. And then once it got to a certain depth, it was just basically stable. It just didn't change much. And that's the natural pedogenesis. That's the soil forming factors that are just keeping it at a very low level, because the biological activity is really near the surface. So we can use this to our advantage. And we know that in the top 12 inches, that's where things are concentrated. And in fact, if we look at just the top 4 inches, we're going to get even a better estimate of the real magnitude of the things that you can do within, say, a decade of time. Because the organic matter changes are relatively slow. We can measure them year by year if we had enough precision, but in fact, it's just really difficult to overcome those variations. So I'm going to explain a little bit about this mathematical concept only because I'm going to show you some data then from the farms in Kentucky of why that I had to go through this process. So this is the mathematical function. It's a mathematical term. I mean, it probably means very little to most people. I mean, if I had seen this for the first time, I wouldn't know exactly what it meant either. So I want to explain a little bit to you about what it is. We can basically put numbers onto these letters that we're fitting. Okay, that's how we're actually making it fit. So the 1 represents the 1% organic matter that is deep in the soil profile. So that's part of the function there. And the 8.8 is the 8.8 plus the 1 that then you see is about 9.8 there near at the surface. So that's how we're actually visualizing and putting the numbers together. And then the rate constant, this minus 3.7, is how steep this occurs with depth. So how fast is it actually decomposing or distributing it down with depth. So that's kind of the basis of the mathematical function. I mean, I know it's boring but it's technical, but it is what it is. In science, I believe, although Ray, I think Ray was okay with that. That science, reductionist science, and all is we need to have pure scientists. Physicists are pure scientists, as my daughter, who graduated in physics, would tell me. That's what she was told. Physics is pure science. Agricultural science, well, that's we can maybe call it science. Okay. But that's what she told me, that's what her professor said, okay? All right. Anyway, but I think we can use some of these concepts. Okay, so the way I'm now translating the concept into reality of how we're going to measure things, okay? We need to know what a baseline condition is because this baseline can vary quite a bit from soil to soil. And so even on your own farm, the baseline can be very different. And I'm going to give you an example of that. But that baseline, that polygon there is what I'm going to use as a baseline condition. Typically in our carbon sequestration type of arrangements, we'd measure a soil now, and then we'd measure it 10 years later and 20 years later. And because I was in the second half of my career, I didn't have enough time to wait anymore. We got to get on with it. And we can get on with it. We can use this concept very effectively, I believe. And then the root zone enrichment. Now the part that you all, when you manage your land, you're focusing on the green portions. You want to increase all of those green polygons. And there are a set of them because I've just broken it down into 2-inch increments. So that we can see that, okay, your biggest effect is happening right at the surface, the first 2 inches, and then that effect declines with depth. All of those could be important, and then we need to sum them up. And that green portion is what you are really focused on. So the same soil profile, I compared it with a soil on the same farm from a neighboring field. And this was a farm in western North Carolina. And the organic matter was very similar near the surface, but it had a very different distribution with depth. So it would be very unfair for me to say the soils sequestered the same amount of organic matter because they started from a different point. One soil was in a bottomland where it had high organic matter deep in the profile, and it had naturally a high organic matter. That soil did not sequester as much carbon as the soil that had very low condition. I'm going to show you why. Okay, I'm going to use numbers, and I'm going to use more numbers, but graphical numbers more so in the rest of the presentation. This is what I'm known for, numbers, okay? Unfortunately, this presentation doesn't have enough photos or slides. But the total stock, in this case here, in the gray line, the one that was the neighboring field, it had 134 tons of CO2 equivalent per acre per 12 inches. Okay, these are the units that are used in the literature for carbon sequestration. Metric tons of CO2 equivalents per acre. Metric per acre. Okay, it's confusing, right? But that's what they use. Okay, it's 134 tons versus 106 in the top 12 inches, above this line here, right? So the soils have an inherently different total stock. But the baseline stock in one case is this narrow sliver, and in the other case is the whole red area. So the baseline condition is different. That's the real point of this whole metric analysis, is that we have soils that start from a different point, and we need to account for that rather than just measure what's in the soil. And so the baseline stock is magnitudinally different. We have more than twice as much baseline carbon. And then we're going to indicate the root zone enrichment, the green areas, and we see that the soil that had this low inherent condition had almost 3 times as much carbon that was sequestered because of recent management. What is recent management? Recent management is in the last 30 to 50 years or so, whatever a generation of farming can do. And you see that this soil on the left is storing more carbon because of management. So if the government ever were to pay you, or if you felt that you had to need to know that what you were doing was good, and that's probably more important than the government paying you anything, because you do it for yourself. You do it for your community. That's what you should be doing it for, not for payment. You can get your payment through better production. I believe that firmly, that if you have better soil, you'll get better production. And the point is that there is a very different amount of carbon that can be stored there. In this case, I'm using it as CO2 equivalents. All right. Now I'm going to get to the results from the farms that I sampled this past winter in Kentucky. So there were, it was sampled from October to March 24, 13 sampling dates. So it was a long period because, Dr. Greg Halleck, who's going to speak after me, he was gracious enough to introduce me to different people. And so we started in October and then we finished up in March. 12 counties, 30 farms, 198 soil profiles. And so that's the region that we're in here, okay? All right, and just divided up into different regions, just because I could. Anyway, 19 fields, 32 fields, 49. This is important because the number of observations becomes important. For statistics are, maybe frightening for some of you. I know it's, but the more observations you can make, the stronger argument you can make that there's a difference. If you make one observation versus another observation, can we say that they're different? You can say that they're different, but statistically, they're not. They're just 2 observations. That's it. But if we had 10 observations here and 10 observations here, all of a sudden we can say mathematically that okay, there's a reasonable condition that they're different or not. And so statistics are important. These are some of the participants that were with me in the field getting samples. And I appreciate all of their willingness to participate. And it's, yeah, Greg, I don't know, this was your neighbor, I believe. Yeah. Anyway, I was just pointing out that the idea is that he's taking the time to look at grass in the field and how it's growing in March. All right, so let's see. There's Greg himself. These are the tools that I bring out in the field. They're actually in the truck. My hands are full. And when I first start, as Matt Poor helped me a couple days ago, also in the field, is and Greg as well, that you have to be conditioned to this. So this is physical condition. This is not a social condition. You can get worn out with this if you're not ready for it. Okay, so the first day I'm not ready for it, and so I'm worn out. All right, but this is important because I'm just going to show you that this probe here is really difficult to get in the ground, but actually getting it in the ground is an important attribute because it gives me an idea of the bulk density or the compaction. And that drill auger there is then important to get deeper in the profile. And that deeper in the profile is important to then create that mathematical function. All right, then each of the farmers is asked to give some management history, and I need this management history because without the actual knowing what happened to the field in the past, the numbers really are just numbers. They don't really tell me anything. So those that still need to get me that management information, please, I hope that you'll get it to me. All right, very good. And this is a depiction, this is not from Kentucky, but this just shows that in cropland we'll have a distribution. It's also fit with this natural logarithmic. Even tilled cropland has this natural logarithmic fit. And the grass systems tend to have just a greater concentration near the surface. So that's the only point. All of the profiles can be fit to this natural logarithm. And I believe that it's just a natural phenomenon. This is just some characterization of the soils in the west, central, and east, and this is the clay content. They're essentially very similar. You recognize this, that okay, they're silt loam to silty clay loam soils. This is what happens in the bluegrass region and the surrounding area. A lot of silt in the soil and a little bit of sand. It's a contrast to our soils in North Carolina. In general, in North Carolina, we have a lot more sand in our soils, and it's easier to work. But for the people that work with me in the lab, the clay and the silt in the soil is just a little more complicated. But I'm glad that I'm not in the blackland region of Texas. Rebecca knows about that area. All right, very good. All right, so this is the soil textural triangle. It shows that all of the soils are kind of similar in the silt loam and silty clay loam, which is covered up there, and a few in the loam and clay loam categories. That's all that's showing there. All right, so I'm going to show you now a kind of a summary across the sites, because I believe that this on-farm sampling requires us to summarize. Unfortunately, I don't think we can really go on to any one particular farm and really get into all of the details of the management. Now, if you had diversity of management on a farm, it's possible that we could go in and take a couple days on your farm and sample maybe a half dozen fields and really sample them very extensively. That is possible, but in this case, I'd rather go with a number of farms. I want to have a dozen of you as farmers to represent a certain management style. That would be better for me, because that's how we would characterize the land from a region, because all of you do something a little bit different, but when we put them into categories together, that makes sense. So in this case here, the cation exchange capacity, well, interesting, the points don't show up, but the lines at least do. You just have to look at the middle point of that. The conventional till, there's really essentially no difference other than in the pasture, it's greater than under no-till cropland on cation exchange capacity. Cation exchange capacity is your calcium, magnesium, potassium, and acidity that's forming these base cations that actually can lead to exchange capacity. The point here is that the bars, the size of the bars, the vertical direction of the bars, the greater the number of observations, the smaller of that bar will be. So in this case here, I sampled a lot of grassland soils and not as many no-till croplands and conventional till croplands. So the bars are increased in size with fewer observations. That's why when we only have a couple observations versus a couple observations, we can't really say that they're different, because the bars are almost always going to overlap. And the overlapping of the bars means that they're not different. That's what we have. We as scientists have to submit our papers to our peers, and they have to agree with it. They have to say that we're doing something, reasonably accurate. Okay. All right, number of field samples. So this shows the number of fields, 79 fields here versus 17. And because of the large number, we can say that they're different. Okay, I'm going to move on to soil fertility of the soil pH. The pH wasn't really dramatically different, but you see that all of the soils were relatively greater than 6. So that's, I think, a reasonable number. You don't need to necessarily fall below 6. But you see, again, there's a significant difference in some of these cases. Let's see, go back to the phosphorus. Yeah, faintly there's the dotted line here, supposed to be a dotted line here, and you see that phosphorus actually, in this case, the woodland has lower phosphorus. There was some mention of phosphorus in the field yesterday too, is that in woodlands, we're not fertilizing the woodlands typically, and so that they can have lower phosphorus. So converting woodland land area to agriculture can lead to low phosphorus, and might be a need for it. But in general, when we have agriculture, all of the soils seem to have enough phosphorus. So that dotted line is kind of like the threshold where there's sufficient levels of phosphorus. Okay, for potassium, all of the land uses basically had enough, because there's a faint dotted line here that shows that they're sufficient. Okay, and as far as aggregation, this aggregation actually was really strong in that grassland soils have, at least in the soils that are sampled here in Kentucky, they have really strong aggregation because you have silt and clay. Those are the two attributes to lead to good aggregation. But you can see that when we have conventional till cropland, it's much lower than under a grassland situation, and certainly under no-till cropland as well. So that gradient shows you that the more intensive utilization of water by grassland soils, by the carbon that's exuded by the roots of those grassland soils, they're keeping the soil strongly aggregated near the surface. Soil test biological activity, you see a strong difference between grassland and the two cropland situations. This is very typical compared with other states that I've been into sampling as well, that the biological activity is enriched with the grassland management. Now, the type of grassland management is important too, and I'm going to get to that in a moment. Okay, as far as the organic matter, the carbon concentration in the top 4 inches is greater under grassland. It's no different than under woodland, but the woodland, I didn't sample many profiles, so there's a large error bar there. And compared to no-till cropland and conventional cropland, there's a difference. This just shows that the intensity of how plants are being produced. When we have no-till cropland, oftentimes it's not with the cover crop, at least the sites that I sampled here in Kentucky. And so there were some that had, but in general, there's a period when there are no roots growing. Again, those 4 soil health principles we need to keep in mind, and that's what's going to contribute to your maximum benefit. Okay, this is where I've calculated the root zone enrichment of soil organic carbon. And this shows it's a little bit different than in this case here, there was no statistical difference between these because this is the carbon concentration of the top 4 inches. This is the root zone enrichment in the top 12 inches, and it shows that there's a trending association here that no-till cropland is potentially greater than under conventional cropland. So the management is having an effect, and certainly the grassland is having an effect more than under cropland. And I'm kind of moving through these because I'm running out of time and I want to be respectful of your time. So the note as far as the root zone enrichment of total soil nitrogen is associated with organic matter just as much as carbon is associated with organic matter. And that nitrogen is bound in organic matter, but it's your bank investment. When you have organic matter in the soil, you get a return on that investment by mineralizing that organic matter. So that the total nitrogen that's enriched in the surface is to your benefit. You have now built up your bank account so that you can get a dividend. You know, it's kind of like those people like me that are nearing retirement. I'm thinking, okay, do I have enough in savings so that I can just live off the dividends? That's where you have value there. And the reason that nitrogen stored in organic matter is important because we can associate soil test biological activity and net nitrogen mineralization together. Now there's no perfect relationship here, but it shows that over the average, if we increase the total nitrogen in soil, we'll increase the net nitrogen mineralization, and we can indicate that with a simple test of soil test biological activity. So that's where we can give value to you to know of that nitrogen that's in the soil, can it actually lead to some profitability in the short term, but also sustainability in the long term. And this biological activity also can lead to an index, it's associated strongly with soil stability index. This is the amount of the aggregates that actually fall apart in the water. So we need to know how stable they are in the dry condition and then how they fall apart in water. All right, so to finalize, I wanted to go through a few scenarios. So pasture management is important, and it really is something that I'll be looking for once I get all of the responses from the collaborators on what they did to the land. So, but in that meantime, I wanted to take you to Virginia. So, and then just to kind of fit in the title of the talk, fiction might be created from a hypothesis, imagination, or a few random observations. I think that this is what I'm trying to overcome in my research, is just the few random observations and the narrative, the groupthink that thinks that carbon can just be stored just because we adopt regenerative agriculture. Now, I don't have anything against regenerative agriculture, but when you say that, I have no idea what you're talking about. Now, Ray, you've given us a definition of what you think, but I don't know if everybody's following those principles or those observations. And so management is really important. What you do to the land is what I need to know to make that connection. And what you need to know also to actually make sense of the data. So I think the facts are what we're looking for. So the facts are the verified repeated observations. So I'm going to show you a similar data set because it was roughly the same number of farms, same number of observations that were out there in a different region. So soils are different in Virginia, but I'm going to show you what I found there. Okay, in this case here, this is soil test biological activity, and we had very low levels under conventional till cropland, intermediate in no-till cropland, and then the highest in woodland. Okay, I said that it was the same, but I didn't include grassland here. Well, I did measure grassland, and I'm going to reveal what those are, but I just wanted to give you the sense that the biological activity showed this gradient here, and that's important to know. But in the grassland, all of the observations are on the same axis here, so almost all of them are greater than under the woodland, first of all. So the soil test biological activity, if you have grassland, you can likely lead to greater biological activity. But the stocking rate can be optimized. So we can have overgrazed situations where we reduce the biological activity. So management is important. And also, if we have ungrazed or very lightly grazed, maybe we're not actually impacting the soil enough. Maybe we're not returning feces and urine back to the soil as much as could have a beneficial effect. And so the biological activity can be optimized at a stocking rate approximately 1 head per acre. Okay, this is rotational stocking stores more soil carbon than continuous stocking, but high frequency moves may not necessarily be better. This is an observation from these farms in Virginia. Okay, that the root zone enrichment of soil organic carbon is low, the no-till cropland is intermediate, and woodland higher, similar as to the soil test biological activity. Again, just to re-emphasize that we can make estimates of different measures here. This happens to be a different measure than soil test biological activity. This is the root zone enrichment of soil organic carbon. I think it's an important aspect to focus on this parameter here. But under grassland situations, I queried the farmers, and almost all of them gave me a response. And they said that I put them in categories of no stock moves, continuous, seasonal, monthly, weekly, subweekly, daily. So moving to the right, there's more intensive moves, more frequent moves. And the data show that, well, there's not a whole lot of difference. Now, there was a slight trend for rotational stocking than continuous, although it actually was not truly statistically different. So to me, the narrative in the literature, and what many would say, is that rotational stocking leads to great things. I think rotational stocking is important. And being at this conference, I don't want to say anything that you don't want me to say. Well, I want to say something that keeps me here living, let's say. Okay, and that's, but the data don't support the idea that rotation and stocking is just going to put you off the roof there, and that you're so much better. So I believe that you can have continuous grazing if you have the stocking rate right. Stocking rate is what really determines the magnitude of change. And so getting that right is important. Okay, the third observation, and I have 4 of them, okay? So nitrogen fertilization on mature pastures may not always be needed, as soil biological activity is an important factor. In this case here, the same trajectory, net nitrogen mineralization. This is how much nitrogen can be mineralized from the organic matter when we put the soil under a condition in the laboratory, ideal conditions. And we have low levels under conventional till cropping because we don't have much organic matter near the surface. It just doesn't have the reserves. No-till cropland is building it up. It's in the intermediate. And woodland has a lot of organic matter near the surface, and it is greater than under no-till cropland. But where is that level under pastures? You can see that the levels under pasture are simply greater than in all other systems. But it's not necessarily positive when you add more nitrogen fertilizer. The fact that nitrogen fertilizer is going to increase nitrogen mineralization in general, at least on these farms, is a misstatement. It's fiction. The facts are that nitrogen is mineralized from organic matter if you focus on building organic matter. It's not whether you give it enough nitrogen fertilizer. In most agricultural systems, nitrogen is not really the limiting factor for mineralization. It's carbon. Carbon, feeding the organisms, is what's really the important part. If you give them the carbon, nitrogen will be mineralized, and there will be net mineralization rather than immobilization. You can get immobilization. Don't get me wrong. These are summary observations. Some of them might have some error associated. But in general, in these Virginia farms, there was no need to increase nitrogen mineralization with nitrogen fertilizer. It just didn't have that effect. Okay, the final observation, soil biological activity can be enhanced with organic amendments, a primary component being imported hay. So this is basal soil respiration. This is during a little bit extended period of time in the incubation where we now are not looking at a flush of activity, but the basal condition. Again, conventional till cropland lowest, no-till cropland intermediate, and woodland the highest. And with the pasture situations where we had, and this was the number of bales per acre that were fed over the past 10 years. And this is an estimation, but the estimation was that, I don't think it's working anymore, but there's an increase with the number of hay bales fed per acre, indicating that maybe there's an opportunity that rather than feeding hay in a certain location in the same pasture at the same time every year, that maybe we could distribute it and actually the pasture would become more productive because it's going to lead to higher basal respiration, which is also related to greater nitrogen mineralization. Now, if I made the association, if I only measured basal respiration, I've never had measured nitrogen mineralization, I shouldn't be telling you that it's going to lead to net nitrogen mineralization or the biological activity there. Because I need to measure, the facts are that you have to associate them. If we only make statements that, okay, because the earth is circulating around the sun, I don't know, I didn't think about this before, but you know, that we're going to go to Mars, okay? Okay, Elon thinks that we're going to go to Mars, okay? And maybe he will, I don't know. But I think that, you know, one doesn't lead to another. You know, we have to have facts, we have to have observations. So this, in this case here, that organic resource, that hay that you're feeding your animals anyway, can actually be a positive benefit on the pasture. Thank you very much.